Hello, my name is Aaron Balke, and in today's video I will be breaking down my linear regression modeling assessment for my Master's of Data Analytics. This assessment does use a theoretical hospital dataset to do the analysis, and the presentation today was made originally for that assessment, and so just be aware there may be some assessment-specific stuff in the presentation. I hope you enjoy. Hello, my name is Aaron Balke, and today I'm going to be breaking down my performance assessment for D208 Task 1, the linear regression modeling. For this performance assessment, our research question is, does total charges correlate to any specific condition? And using a multi-regressional model, we'll be able to see how total charges correlates to multiple different conditions and different portions of the data set we have. And so the goals of this analysis is, in many situations, healthcare in particular, financial burdens of our products and services can be overwhelming, and we want to find a correlation between total charges and specific conditions in order to help patients cost estimate, relieve financial uncertainty, and doing that should make our patients' lives easier and our lives easier through that. So it'll help our patients, which will help us out in the long run. Using the multiple regression model will allow us to make informed decisions on that and provide estimates, resource allocation, all of that good stuff. So, for our methods, some assumptions about the multiple linear regression model. There has to be a linear relationship. If there isn't a relationship, there's no point in doing all of this. So there has to be a relationship of some sort between the independent variables and the dependent variables. If there is not a relationship, we don't include those values those variables inside the data set. The second assumption we have is that the residuals are normally distributed. The variance of those have to be all normally distributed in the data set. And then no or little multi-collinearity. We don't want the independent variables to be perfectly correlated with each other. If we have that, then that can lead to false negatives, and it's sort of like doubling up the power of that variable and can cause issues with the regression model. And finally, independence. We want each variable to be independent from other variables. That's similar to the multi-collinearity and falls under the same sort of problems that can occur. The tools we're going to be using today are Python and Jupyter Notebook. We're using Jupyter Notebook version 6.5.2 and Python version 3.10.9. The reason we're using Python is, in particular, its strong module library support. In our analysis, we're going to be having to deal with variance inflation factors, a OLS method from, I believe it's stats models. Yes, from stats models. And we wouldn't have access to those methods directly without the library support that Python provides. And being able to have a language with that sort of library support will make it possible to automate and remove a lot of the unnecessary maths, really, of the entire process. So that's the reason we're using Python. We're using Jupyter Notebook because it is Python is the default language for Jupyter Notebook. Jupyter Notebook gives us access to stuff like checkpoints, which allows us to save file states. It allows us to, let's say, run the initial OLS model that we create and then go back to it later without rerunning the entire program again. It allows us to save the state of different models for access later. And that's going to be important when these models get bigger and bigger. We're going to want to be able to access the results of those models without rerunning them every time. And since we're using a multiple linear regression model, we are going to need continuous variables and categorical variables. The total charges is provided as a float number, a continuous variable. And so that's why it works as our dependent variable. So before we get started, I better make sure this actually runs. So we'll run the entire book here. Maybe not. Hello. There we go. So while that's running, we can start going over the data preparation stuff here. For the cleaning of the data, what the main goal of the data cleaning is, so the data we have is the medical clean data set. And so it's removed a lot of the outliers and stuff like that. So the main goal of our cleaning process today will be to remove unnecessary information, remove duplicates, remove missing values, anything like that. We're just wanting to filter everything, get down to the data set that works for our analysis. Let's see if it finished running all this. 16, oh, just switched there. Okay, so I got down to the final one there, so it all works. So when it comes to importing the data and the libraries, we got a bunch of standard ones here: Math, NumPy, Pandas, PyPlot, Seaborn. For this specific analysis, the additional ones are stats models. So the SM here allows us to use OLS regression methods and modeling. The variance inflation factor will allow us to evaluate our model and make it more accurate and remove unnecessary variables. So that's what those are for. And then we just import the data here. When it comes to cleaning, the first thing we're going to do is check for duplicates, which we do here. And we can see that there are 0 records in the data set that are duplicated. So good news, we don't have to worry about duplicates. Then when it comes to checking for null values, we sum up all of the null values for each record. And then we do we run that against the data set just to we reverse it in order to just get out how many null records there are, which the shape comes back as 0, so we have 0 null records in the data set as well. So don't have to worry about either of those. And then we just drop the columns, the features we don't have to worry about. And I removed a bunch of the survey results, a lot of the population demographic stuff. So case order, customer ID, interactions, state, country, and then the survey stuff, item 1, item 2, item 3, item 4, item 5, item 6, item 7, item 8. So just remove those because we're not going to need that for our multiple linear regression model. Then we have the summary statistics here. I decided to break it into 3 sections. We have the first portion here, which is just getting the summary stats for the dependent variable. So for total charges, we just run describe on it. We get back the count, mean, standard deviation, minimum, maximum, and the quartiles. I didn't see anything sticking out to me here. We got then the continuous independent variables. We have continuous independent variables and then categorical. The reason I split those up is because you use different methods on those features in order to get information. So for the continuous variables, we got run the same describe method on these. We get the count, mean, standard deviation, minimum, maximum, and quartiles for all of these variables. From previous analysis, I was able to know that the minimum for age would be 18. The number of doc visits starts at 1. So there's a few stuff like that stick out. Nothing too crazy here other than that. For the categorical qualitative independent variables, we then run value counts on it. And that method tells us for each category how many records fall under that category. So for marital unique values, we got it separated by widowed, married, separated, never married, and divorced. And that sort of gives you an idea of what we're doing here. Go down here. These are all of those categorical variables. Very many. And then we're on to the distribution visualizations. The first couple we got are univariate distributions. So we will start with the dependent variable, which is total charges. When it comes to total charges, we do see a large amount of patients sitting in this lower hump here, and then another big group here at the second hump. And so it's sort of split into two separate groups. You kind of got the lower amount charged and the higher amount charged. And so it'll be curious to see with our multiple regression model what sort of splits the patients into this lower and higher amount. I then ran the same sort of the same sort of histograms on the continuous variables, the continuous independent variables, and the categorical, excuse me. And I got a pretty tight of a group of plots here. So we just got each model. We have 10 bins for each just to see the distributions of the patient frequency across each variable here. And so we got all of that here. A couple observations I made. Additional charges, which is this one to the right over here, has a steep cutoff at 15,000. So you have a lot of people getting charged additional charges between 0 and 15,000, and then you still do have a couple after 15,000, but the amount is much lower. The other one is age. Let's see here. Age is very evenly distributed. There's within 100 patients, 100 records for each age group, and I've got it split into pretty much a decade each. And so I was kind of thinking in my head that the older patients, there would be a lot less older patients than younger patients, or depending on the area, you know, it's very rare that you would have a very even distribution with age. That's, from my experience, not a normal thing. So that was just something I noticed when I was taking a look at our data set. Then we got the bivariant visualizations, and so we're just comparing each independent variable against total charges. So very similar, except for we're running scatter plots for each of these. It's a bit hard to see, but you can kind of see with, for example, the total charges and initial days, you can see a strong correlation between the two. So when they're following a strong diagonal line, either positive or negative, that kind of implies a strong correlation between those variables. So we definitely see one here with total charges and initial days. We also see over here with total charges and readmins, we see a strong correlation there. These ones are all pretty distributed evenly. Total charges and initial days are correlated. Readmins and total charges are correlated. And there does not seem to be a correlation between age, which is the center top one, and total charges. And you kind of would have thought that, at least what I was assuming, that the older patients, you know, have longer hospital stays. Most likely the older patients have more intense and more invasive treatments because that's what happens to old people. And so that's just something I assumed, and I'm wondering if we saw how evenly our age distributions were. Maybe that plays a part in that. Just something to think about as we're moving forward with our analysis. The next step will be to transform the data. We're going to want to convert categories into the different data types into the correct ones. So we got categorical data types that, you know, those are objects, I believe, is in data frame lingo what they're referred to as. They're pretty much just strings. And so we want to convert those into categories. We want to convert Booleans from yes and no strings into ones and zeros, binary values. And I just put the numeric ones in here so we kept track of which variables were which. The other important thing when it comes to data transformation is dummy variables. And so what a dummy variable does is it takes the categorical variables, here let me show the code here, it takes the categorical variables and splits them into binary values for each category. And so the example that the easiest example is the gender, which is female, male, or non-binary. And for female, male, non-binary, when you split that into dummy variables, you have a male 0 or 1, a male Boolean value. Are they male, yes or no? If they're if it's a yes, then they're male. If they're not, then they're either female or non-binary. And then from there, you say you have a female column, for example. And so you're able to tell from those dummy variables who if someone is male or female or non-binary based on just 2 columns. And so it's important to remove the additional column. So in that example, we would have taken out the non-binary column just because if they're not male or female, they must be non-binary. And we do that because we want to make sure we don't have multi-collinearity, as we mentioned before with assumptions in multiple linear regression. So we do that by splitting them into using the dummy variables. That is what's required for the multilinear regression model. We can't use the string category yeses and nos and female, male as values. We have to use zeros and ones. So that's what's going on here. And we got the export data. The data is exported into a CSV here. That's the cleaned up data set. And then on to the actual modeling and analysis. So the first step here will be to create an initial multiple regression model. And so we set y, the y as the total charges, and we set the x as all of the independent variables. We also do assign a constant, so we have a constant of 1. We could have thrown this in as another feature, just a constant feature of the data set, but it's just simpler to do it here. So we just set 1 constant into our data, and that allows it's in that's our the constant is the easiest way to think about is the when you have a mx plus b slope, just a simple line, you want that y to set how far up and down the value will start at the at 0x. And in our situation, when we're talking about total charges, that constant is sort of it is the value that everyone starts at when it comes to total charges. That's sort of our constant amount that everyone's going to be charged right off the gate. So I can't remember off the top of my head the amounts, but let's say if everyone coming in has to get charged 1,000, that's where it would start. It would start at 1,000. But we'll see what the actual amounts and all are there at the end of the process. This is just an example. We throw this into the stats model OLS, multiple regression modeling method. An object, throwing that in creates a model. We fit it to the X values. That comes out with results, and this is a summary of those results. So important things to notice, we are at a R² value of 1, which is really awesome, but we do have 35 variables we're keeping track of, which is a lot of variables. So these are all of them in here. The next step will be to start removing variables. We want to get rid of any variables that are not important to the multiple linear regression model. That's another one of those assumptions. If there is not a relationship between the independent variables and the dependent variable, we just want to get rid of those independent variables. And the method we're going to use to do this is use that variance inflation factor. What that will do is any value over 10 for a variance inflation factor, we want to remove because that feature is either, it's too heavily correlated to other features. That falls under that multi-linear collinearity, excuse me. And so we're going to go through, that's what this is here. I made a nasty little regression function here, a recursive function, excuse me. And so what it does is goes through, creates a data frame of the variance inflation factors and names the feature for that variance inflation factor. It sorts all of them by the variance inflation factor and gets the last one. If that last value, the one with the highest value, is over 10, then we remove that from the data frame, the variance inflation factor data frame, and we remove it from the variables and our data set. Once we remove it, we run this all again because the variance inflation factors change each time you remove a variable. And so you have to run this entire process every time you remove a variable. And we do that until we don't have any variables more than 10. Once it's done there, it stops running the function and we get out of that loop. And so this was a fun little thing to come up with. I was proud of this one. So what we did was we removed additional charges because it had a VIF value of 78. We removed vitamin D levels because it had one of 33. Then we removed doc visits because it had one of 14. And then we removed all of the ones over 10. There were no more. I believe the next one, from what I remember, was age, and it had a value of 6. So we don't need to remove that one. After we remove all those variables, we run the OLS model again, same story, and we get results here. We're down to 32 variables, and it is continuing to be an R-squared value of 1. At this time, we want to check the variables and see which ones are not important for our model. We want to remove anything that doesn't really have a relationship with our total charges dependent variable. And the way we're going to do that is check the p-values. What we do is we sort the p-values and then just get a list of all of the p-values greater than 0.05. This falls into it. We can be 95% sure that a p-value, if a p-value falls below 0.05, we can be 95% sure that value is important to our model for our OLS model. Anything greater than that is not, and so we want to drop those features. And so we just do that. We get the names of the dropped features, and we drop that from the data frame. We also remove it from my variable I'm keeping track of the independent variables with. So we remove that here. Then we got the final model here. Same story, set up the same way we have the other 2 times, but we're now down to 12 variables because we removed is that almost 20 variables that were too high of p-values that were not did not have a relationship with our total charge dependent variable. And as you can see, the R-squared value is still 1. So we are able to keep with just 12 variables the same R-squared value, but we're significantly down from the 52 variables we started out with. And so comparing the models, we do have the same exact R-squared value, but with only 12 variables as opposed to 30 or 50. One thing that I did notice in my research and all, I wanted to use the adjusted R-squared metric, which is this value here. The adjusted R-squared metric is a R-squared value, but then it gives you a lower score the more it penalizes you, that's the word. It penalizes you based on how many variables you have. So if you have 100 variables and only 4 of them are important, it's going to give you a very low adjusted R-squared value. And in our situation, what I found a little bit weird and had to do a little bit more research on is that we have a adjusted R-squared value of 1 for all of the models, which is not how it should work. This first model we did should have had a lower R-squared model. And so after some exploratory data analysis, some additional work I did, some work on checking out correlations between different variables, what I realized was that the I believe it's the initial days variable. Yes, the initial days variable. This one is correlated with the dependent variable, the total charges, a bunch. And while that's not a problem for building the multiple linear regression model, what happens is whenever you remove or add variables to the model, this heavily correlated initial days variable will just adjust based on that. It will just adjust based on the it will change based on the variance in order to make up for any problems with the variance. And so when I removed this initial days variable from the independent variables, then we did start to see the adjusted R-squared model change depending on the amount of variables. But the way we've got it built now, the initial days will just adjust in order to keep the model at 1.0 for the R-squared and adjusted R-squared. I decided in our situation that's probably all right. That's not that big of a deal, so I'm going to keep it in there because once we took it out, the highest R-squared value we could get was a 0.732. So I decided it was more important to have a more accurate model than it was to take that out and have a adjusted R-squared value that changes between the models. Removing the variables is still giving us the same output, the same goal of doing the reduction of the variables. So that's just something to keep in mind. I had to do a lot of research to figure out why that was happening, but the short of the long story is the adjusted R-squared value is the best metric. However, in our situation, the initial days variable will keep it always up close to 1. So that's what's happening there with the final model. And we're down to just 12 variables, so we were able to reduce the model very nicely and keep a R-squared value of 1. Then for model analysis, we got all the residual plots here. It ran for each variable in our independent variable. So for each independent variable, we run a plot on the residuals. Pretty much we want to keep all of the residuals on the line as much as humanly possible. For these red values, we want the red and blue to pretty much overlap. We want the for the other graphs them to be on the line. Some of these residual ones, such as this residuals against initial days, the top right one here, it's important to take note of the size of these residuals. So these are very small residuals, even though the graph makes them look very big. So that's something to just keep in mind. It's also important to realize, as in this situation, initial days changes, the magnitude, if the magnitude of the variable changes, the magnitude of the residuals will change as well. So that's another thing to keep in mind there. And the final, when you get all of the residual error for the entire model, we come out with 0.00026. So very little residual errors. The next step was to create a executable code. I'm not sure if the Jupyter Notebook itself is enough to meet that requirement of the performance assessment. If not, I did create an additional Python file that can be ran. The only caveat with that is, in order to run the file, you do need the NumPy, Pandas, Matplotlib, Seaborn, and stats models libraries installed either in your Python environment or on your machine itself. So that file is available if this is not enough. However, you do need those additional libraries. Then for the summary of our analysis and the implications of our analysis, we are able to create a nice little equation here of the how to figure out the total charges from those independent variables. And so that is here. It's also very handy because all of these amounts are provided as they're equal to dollar amounts in our situation. And so if you need a practical interpretation of this model, you can say a patient's total charges can be interpreted as all things constant, a patient will be charged $2,269.18 by default. So if you walk in the door, we can immediately estimate that as the starting point. Then for each day you're in the hospital beyond that, it's another $81.94. And then if you have high blood pressure, we add another $112.32. If you have arthritis, another $71.95. If you have diabetes, another $75.20. If you have hyperlipidemia, then you get another $93.99. If you have back pain, we can add another $85.14 on there. If you have anxiety, we charge another $96.11. If you have allergic rhinitis, you'll be charged another $60.58. If you have reflux esophagitis, there will be another $59.68. If you're in an emergency, if that's why you came in, you're going to be charged another $512.32. If you have low complication risk, we can remove $413.49 from your charges. And if you have a medium complication risk, we can remove $413.49. And so that's sort of the practical interpretation of the model. The handy part about this is from here, we're able to make a really nice estimate for our patients when they walk in the door, or if they're wanting to do an estimate before coming in. We can really just give them a 12 question estimate where you just say yes or no to these situations, and then we can provide an estimate to our patients and assist them with estimating costs for future visits, all of that good stuff. And the probability F statistic and R squared values are showing that we're accounting for all of the variance in the model, and it's pretty much a perfect model. Some limitations of the model. It is important to realize that this is a generalized model for what I'm assuming is the entirety of the United States. So that is something important to keep in mind. Is I'm sure there's, for each region, a little bit different. Someone in Montana is probably getting charged differently than someone in California. The cost of living and all changes the prices being charged in those different locations. So my recommendation will be we'll just talk about the recommendation now. My recommendation will be to use this model to create estimates for patients. However, more research needs to be done if we need to do specific estimators for each region, geographically, culturally, all of that sort of stuff. So that will be my recommendation. However, the other limitations we have to worry about are particularly the Boolean features might be better suited as continuous variables. It's a little bit easier to figure out if have a exact amount for like high blood pressure than to have a yes or no question. Do you have high blood pressure? Because I'm sure depending on what hospital you're at, the threshold for high blood pressure can change, and so our patients may have a different threshold as well. And along those lines, the subjectivity of the variables, if you just ask a patient, do you have high complication risk? I mean, that for some people will be obvious, but some people won't be sure. So stuff like that is important to keep in mind as well. And we talked about my recommendation already. That is my multiple linear regression modeling using Stats Model, using Jupyter Notebook and Python. I really liked this one. I liked the ability as the accountant in me. I've been doing accounting for many years, so being able to have something like this was just beautiful. This reminded me of IRS documents, so this was fun to do, and I hope to have fun with task 2 as well. Hope you enjoyed it, and have a good one.